Hello, I'm Jisung Park, a postdoc in software research group at ETH Zurich, and I'll talk about our work to improve SSD read latency by optimizing read-retry. This work was done in collaboration between Software Research Group and Seoul National University, and it appears in ASPLOS 2021. This is a high-level summary of our work. In this work, we tackle SSD performance degradation due to read-retry that frequently requires multiple retry steps for reading an erroneous page. Our goal is to reduce the latency of each read-retry operation, and we propose two new read-retry mechanisms. First, we introduce a pipelined read-retry, PRScale in short, that concurrently performs consecutive retry steps using the advanced cache read command. Second, we introduce adaptive read-retry, ARscale in short, that reduces the read timing parameters for every retry step by exploiting the reliability margin provided by strong error correcting calls. Our two techniques can be implemented in the flash controller at low cost, requiring no changes to underlying NAND flash chips. Our proposal improves SSD response time by up to 51% compared to a high-end SSD, and by up to 32% compared to a state-of-the-art read-retry mitigation technique. This is the outline of my talk, and I'm going to start with a brief overview of read-retry. NAND Flash memory stores data by adjusting cell threshold voltage values. This figure shows a part of the threshold voltage distribution of a page, where each threshold voltage state can be distinguished by using the corresponding read reference voltage values. For example, if we apply a certain read reference voltage value to the target cells to read, some cells would operate as a resistance if the cell's threshold voltage is lower than the applied reference voltage, while the other cells will operate as an open switch since the cell's threshold voltage is higher than the reference voltage. So you can specify any threshold voltage state if we read the cells twice with two read reference voltage values. For example, in this figure, the cells in state Px would operate as a resistance if we sense the page using the left read reference voltage, but the cells operate as an open switch if we use the right read reference voltage. In contrast, the operation of the other cells would not change, meaning that the other cells would consistently operate as either a resistance or an open switch, no matter which of the two read reference voltage values is used for reading the page. In NAND flash memory, various error sources like retention loss, program interference, and read disturbance shift and widen programmed threshold voltage states. If a cell's threshold voltage value moves beyond the corresponding read reference voltage, reading the cell incurs an error. And this happens quite frequently, meaning that modern NAND flash memory is highly error-prone due to the narrow margins between threshold voltage states. For this reason, it is common practice to use error correcting calls in modern SSDs, which basically store some redundant data called ECC parity, along with the original data in order to use the redundant data for error correction. Typically, the ECC engine exists in Flash controller, and when the SSD controller issues a read request, for example, to page 0 in this figure, the Flash controller issues a NAND Flash command with the page address. Then the sensed data is transferred from the chip to the flash controller, and finally the ECC engine decodes the transferred data, trying to correct all the raw bit errors in the page. However, if the number of raw bit errors is higher than the ECC correction capability, it incurs uncorrectable errors in stored data. To address this, modern SSDs commonly adopt read-retry, which reads the page again with adjusted read reference voltage values. As shown in this figure, using properly adjusted read reference voltage values significantly decreases the number of raw bit errors in reading the page. Unfortunately, read-retry also significantly increases the read latency. Reading a page consists of three steps: page sensing at the chip, data transfer from the chip to the flash controller, and ECC decoding at the flash controller. If the number of bit errors is lower than the ECC correction capability, the read request can be returned immediately after ECC decoding. However, when the number of raw bit errors is higher than the ECC capability, the flash controller performs multiple retry steps until it reduces the number of bit errors to be lower than the ECC capability. This in turn increases the read latency almost linearly with the number of retry steps. To understand the performance impact of read-retry in modern SSDs, we measure the number of retry steps under different operating conditions by using more than 10 million pages from 160 real 3D triple-level cell NAND flash chips. Here we perform the real device characterization at 3 different program and erase cycles, let's say 0, 1K, 2K P cycles. For each P cycle count, we tested the chip while changing the retention age of the pages, meaning while changing the elapsed time since the pages were programmed from 0 to 12 months, as shown in the x-axis. The y-axis shows the number of retry steps per read, and each cell in the plot represents the probability of a read, incurring the corresponding number of retry steps using different colors. For example, under a 6-month retention age at 0 P cycle, a read request incurs 5 retry steps with a probability of around 40%. In this experiment, we observed that under high P cycle count and long retention age, the number of read retry steps significantly increases up to 25 retry steps. In fact, we can easily expect this since it is well known that program and erase cycling continuously damages flash cells, and a flash cell inherently leaks its charge over time. A new observation in our experiment is that many reads require multiple retry steps even under modest operating conditions. As shown in the plot, every read requires at least 3 read retry steps even under only a 3-month retention age at 0 P cycles, which means that the reader latency significantly increases by more than 3 times compared to when there is no read retry. To mitigate the performance overhead of read-retry, prior work has proposed various techniques that basically aim to reduce the number of retry steps by accurately predicting near-optimal read reference voltage values. As explained, read-retry is a process to find the near-optimal read reference voltage values that can reduce the number of raw bit errors to be lower than the ECC capability. The basic read-retry mechanism gradually adjusts the read reference voltage until it finds ones close to the optimal values. Prior work attempts to predict near-optimal read reference voltage based on error models, which allows us to skip unnecessary retry steps. However, the threshold voltage states quickly and significantly change over time in modern NAND flash memory, so read-retry is a fundamental problem that is hard to completely eliminate. Next, I will present our first technique. Our first key idea is to concurrently perform consecutive retry steps. This is the baseline read-retry mechanism. And using the cache read command, PRSquare speculatively starts the next retry step as soon as the page sensing of the current retry step is finished. This idea is quite simple, but can significantly reduce the read-retry latency by removing data transfer and ECC decoding from the critical path, which contributes almost 30% of the latency of each retry step. However, PRSquare can also negatively affect SSD performance by speculatively starting additional retry step, which is in fact unnecessary to perform. This happens because PRSquare cannot know whether a retry step succeeds or not at the moment it issues the next retry step. Since such an unnecessary retry step can delay future requests by making the chip busy, PRSquare terminates the unnecessary retry step as soon as the ECC decoding of the previous retry step succeeds. All this process is done by the flash controller and does not require any changes to underlying NAND flash chips. In summary, PRSquare can significantly reduce the read-retry latency with a negligible performance penalty. Next, let me present our adaptive read-retry. This figure shows our pipelined read-retry mechanism, and you observe that there always exists a positive ECC margin in the final retry step when read-retry eventually succeeds. In this figure, for example, we can see a large ECC margin since there are only 23 bit errors in the final retry step, while the ECC can correct up to 72 bit errors. ASPLOS exploits this ECC margin to reduce the read timing parameters, meaning the page sensing latency, for every retry step, which further reduces the read-retry latency. However, reducing read timing parameters would inevitably increase the number of raw bit errors, So we need to ensure that the number of the additional errors does not exceed the ECC margin in the final retry step, because otherwise the ECC decoding of the final retry step would fail. So AR scale would be feasible under two conditions. First, there should be a large ECC margin in the final retry step. We expect that this is the case since modern SSDs commonly use a strong ECC, and in the final retry step, the read reference voltage values should be quite close to the optimal values, because otherwise the number of raw bit errors cannot be sufficiently reduced, as it drastically increases if we use far optimal read reference voltage values. Second, there should also be a sufficient reliability margin in read timing parameters. We expect that this is also the case because manufacturers pessimistically set read timing parameters to cover for worst-case process variation and operating conditions. We experimentally analyze if these conditions hold. We rigorously characterize the ECC margin in the final retry step and the reliability impact of reducing read timing parameters under different operating conditions. We evaluate more than 10 million pages that we randomly select from 160 real 3D NAND flash chips using an FPGA-based custom flash controller that supports test mode commands such as changing read reference voltage values and read timing parameters, as well as the basic commands like page read, page write, and block erase commands. This graph shows the maximum number of raw bit errors in the final retry step that we measure under 3 different P cycles and 5 retention ages. The x-axis shows the retention age, and each line shows the result for different P cycles respectively. We assume ECC that can correct up to 72-bit errors per 1 kilobyte data. We make 2 key observations from the plot. First, there is a large ECC margin in the final retry step, even under worst-case operating conditions, which means that the first necessary condition for AR scale holds. Second, the ECC margin decreases as the P cycle count and retention age increase. Next, we evaluate how read timing reduction affects the number of bit errors in the final retry step. Here, the x-axis shows that the reduction amount of the page sensing latency, and each line plots the maximum increase in the number of raw bit errors in the final retry step under 4 different operating conditions, respectively. We also mark the safe reduction points for 2 operating conditions in the plot. As we expected, the second necessary condition for AR scale also holds, as the results show that there is a large reliability margin in read timing parameters, which enables at least a 25% reduction in the page sensing latency even under worst-case operating conditions. We also observe considerable variation in the reliability margin depending on operating conditions. Based on our observations, we confirm that AR scale can easily work in state-of-the-art NAND flash chips since all the necessary conditions are met, but we must properly reduce the read timing parameters depending on the current operating conditions. So let me review the overall read-retry process when we combined our PR scale and AR scale. We first propose SSD manufacturers to incorporate a read timing parameter table into the SSD so that the SSD controller can get the best read timing parameters depending on the current operating conditions from the table. This can be done easily and accurately by the manufacturers since they already have a sophisticated infrastructure for profiling a large number of NAND flash chips. When the ECC decoding of our read request fails, our proposal first queries the read timing parameter table to get the best read timing parameter under the current operating conditions, which is smaller than the default value, but would not increase raw bit errors to be larger than the ECC correction capability. Then the SSD controller sets the read timing parameters using setFeature command, which takes only less than 1 microsecond, so that all the retry steps are performed with the reduced timing parameters. The SSD controller starts the first retry step using the regular page read command, while speculatively issuing the subsequent retry steps using the cache read commands. Once the ECC decoding succeeds, the SSD controller immediately terminates the ongoing retry step using the reset command to minimize the performance penalty due to the unnecessary retry step. Finally, the SSD controller rolls back the chip's read timing parameter to the default value for future read requests. This OR process neither requires changes to underlying NAND flash chips nor affects the threshold voltage values of the read page, so our proposal can be easily adopted in modern SSDs combined with existing read-retry mitigation techniques that reduce the number of retry steps. Next, I will present our system-level evaluation results. We use a state-of-the-art SSD simulator called MQSim by extending its NAND flash models with our real device characterization results so that each simulated page shows the same read-retry behavior as one of the tested real NAND flash page. We use 12 real workloads, 6 from MSRC traces and 6 from YCSB. We compare our proposal to 3 baselines: an ideal SSD where no read-retry occurs as the upper bound of SSD performance, a high-end SSD without any read-retry mitigation, and a state-of-the-art read-retry mitigation technique that reduces the number of retry steps by predicting near-optimal read reference voltage values. We first compare our proposal with the high-end SSD baseline. This plot shows the response time of each compared SSD under 3 operating conditions, which is normalized to the high-end SSD without any read-retry mitigation. Here, PNAR2 stands for our final proposal, pipelined and adaptive read-retry, and MSRW and MSRR on the x-axis refer to the write-dominant workloads and read-dominant workloads of MSRC benchmark, respectively. As shown in the plot, our proposal significantly improves the SSD response time by up to 42% and 26% on average. We also observed that our proposal achieves a considerable improvement in write-dominant workloads by optimizing read-retry operations that are introduced in garbage collection process. Next, we compare our proposal with the state-of-the-art read-retry mitigation technique. When 2 techniques are applied exclusively, the state-of-the-art technique, which aims to reduce the number of retry steps, provides a higher performance improvement compared to our proposal. However, when we consider the optimal SSD performance, the state-of-the-art technique alone also shows a significant gap from the optimal performance. As explained, our proposal introduces a very small overhead and it is independent of the existing technique, as our proposal reduces the latency of each read-retry step while guaranteeing the same number of retry steps. So we evaluate the performance of an SSD that integrates our proposal on top of the state-of-the-art read-retry mitigation technique, and the results show that our proposal further improves the SSD response time by up to 29%, reducing the gap from the optimal performance. Please also see our paper for more detailed analysis and evaluation. There we thoroughly analyze the read mechanism in modern NAND flash memory and provide much more detailed real device characterization results, including the effect of reducing each timing parameter individually, the effect of reducing multiple read timing parameters at the same time, and the effect of operating temperature, and finally the methodology to choose the best read timing parameters. We also evaluate the effectiveness of PR square and AR square when they are individually adopted and discuss the future directions to further reduce the SSD read latency based on our insights in the paper. Finally, I'd like to conclude my talk with a quick summary. We tackle long read latency in modern SSDs due to read-retry, and we propose 2 new read-retry mechanisms that reduce the latency of each read-retry operation by exploiting the advanced cache read command and high reliability margin in modern SSDs, respectively. Our evaluation shows that our proposal significantly improves SSD response time, especially complementing the existing techniques that reduce the number of retry steps. We hope that our key idea and real device characterization results inspire many valuable studies going forward. Thank you. And if you enjoyed my talk, please take a look at our full paper.